Okay, recording is going, so I will rewind. So today we're going to talk about phase-sensitive detection, and this is the part that I left out when we were talking about the signal equation, because in talking about the signal equation, we said we've got these precessing protons. They generate this oscillating signal in a coil, but how do we actually get sort of the vector quantity, the two-dimensional complex valued quantity out of a single stream of numbers? At each point, you have a complex value, the two components, like an x and a y component, real and imaginary component. And so how is that done? And that can be done with a single coil. So you just have one stream of numbers, and the phase-sensitive detection turns it into two streams of numbers, and you actually get a vector quantity out of that. So that's what so how is this done? So this is, what I'm talking about is not rocket science. It's very old technology. This has been around for like 70 years. It's critical technology for doing like FM radio, for instance. And all the technology that I'm talking about came from before MRI imaging. Magnetic resonance imaging, MRI, is what we're talking about, but all the technology for this came from the chemists, from people sort of adapting FM radio technology to record nuclear magnetic resonance of chemicals. So this is very old technology. And if you look at a typical psychology MRI class, they never talk about this, and the reason is because it's a little technical. It's not that technical. It's a little technical, but if you don't get this, then literally the whole thing just doesn't make sense. And so that's why I really take a whole lecture to go over it. And so another way of thinking of this is how we get the rotating frame. So essentially what you're doing here is you're basically transitioning into the rotating frame, and the signal you get out is a signal out of the rotating frame after you've done phase-sensitive detection. So how does this work? So the basic unit of phase-sensitive detection is the following thing. So we have a single voltage. So that guy, this guy is just a number. It's just so that this is not it's a scalar. That's a number. It's not a complex number. It's just a real number, and it's whatever the instantaneous voltage coming out of the coil is. So, what are we talking about? We're talking about, we've got some, head in the coil. There's a head in the coil, and here's our coil. And we're talking about what we get out of the terminals of the coil. So the coil is going to give us a voltage at each point in time. That's just a number. And so that voltage is typically going to be something that's oscillating around. There'll be different frequencies in it, but it's going to be typically oscillating, around our 2.9 Tesla magnet. So that's, 123 megahertz. So 123 million oscillations per second, up and down, with multiple frequencies in there, but all added together into just one stream of numbers. So the fundamental way that phase-sensitive detection works is that you do a multiplication. And so how do you multiply a current? I mean a voltage. How do you multiply a voltage? You multiply a voltage by using an amplifier. That's what an amplifier is. It's a multiplier. It takes one input, and that input multiplies the output of the amplifier. So you electrically multiply this input signal by a reference signal. And so here's the reference signal. And so this guy's about 123 megahertz, not exactly, or it could be up or down, changing over time. This reference signal, equals your center frequency. And we'll just say that for now we've set the center frequency to exactly 123 megahertz. So we multiply by that signal. And then we take the output of that, and then we do what's called a low-pass filter, which means get rid of the high frequencies, and then we get a signal out of that. So this is our basic sort of phase-sensitive detection device. So it basically multiplies our input signal and then filters out some high frequencies. So why are we filtering out the high frequencies? So, and then what we get out of that is a signal in time, and this guy's still just a number, scalar. You know, scalar, single number, not complex. So we're not done yet, but this is the basic phase-sensitive detection unit. So what does this do? This is basically a way of moving from these very high frequencies, 123 megahertz, down to a much lower frequency. And there's various sort of jargon for describing this. You can describe this as sort of moving to the bass band sometimes. You can also describe this as demodulation. So there's a lot of modulation going on here. We're sort of like getting rid of most of the modulation. Those you might see demodulation or the bass band as an idea here. And so when we get this thing here, this thing is changing much less rapidly than this. And so we have to digitize this. So we have to sort of turn it into a stream of, computer numbers. And so we might digitize it at, say, 100 kilohertz, kilohertz, not megahertz. So we're only collecting 100 samples, 100,000 samples per second instead of 100 million samples per second. Now, nowadays it turns out like cell phones, because of cell phone technology, you've gotten the ability to digitize signals, like turn an analog current into an analog set of voltages into numbers at the megahertz range, 100 megahertz range. But we still do it this way in the magnet. This is kind of the old tried and true way, from 1950. So what does this do? So for this, we have to sort of look at. This is the one place where trigonometric identities that I learned and completely forgot when I was like in 10th or 11th grade. It's an actual use for them. So here's the demodulated signal. So that's this guy. Demodulated signal is proportional to, there's some constants in there we don't have to worry about. So it's proportional to basically the RF coil signal times the reference signal. And what is the reference signal? The reference signal is coming from the RF transmitter. So this is from the transmitter. The transmitter is the thing that sort of defines what time t equals 0 is. And that's basically, it's basically information from the transmitter oscillator is what's actually going to provide this extra information that will allow us to get two numbers out of this single coil. So if we just think of this, as just it's not a sine wave because it's got like multiple, sort of it's a sine-like wave, but it's changing over time. It's got multiple frequencies added together to make a sine wave. Let's just idealize it as a sine wave. So it's a sine wave of our center frequency. So that's the center Larmor frequency, but there might be a frequency offset in it. So we have, here's a frequency, a delta omega, a frequency offset, and then the frequency is cycles per second, or as angles per second, radians per second. But then we have to multiply it by time in order to get an angle, because we're taking the sine of an angle. So we're then multiplying that by our transmitter, which is exactly at the center frequency. So here's the transmitter. So there's the center frequency times time to give us an angle at a moment in time. So this is demodulated signal at moment in time. Okay, so that's our equation. So what can we do with this? Well, we can use some trigonometric identities, and so here's two of them. So here's if we take sine, sine A times sine B is equal to 1/2 cosine of A minus B minus cosine of A plus B. And here's another one. So the sine times cosine. So what about sine A times cosine B? So that's 1/2 sine A minus B plus sine A minus B. Oh, A plus B. A plus B, yes, plus. Okay. So if we use those, then we can rewrite this guy, depending on whether we've got a sine or a cosine. So I'll just write it, we're just assuming we've got a sine. So then this one's going to be proportional to 1/2 cosine of the frequency offset times time. So there's cosine of that thing. Minus cosine of 2 times the center frequency, plus the offset frequency, which is negligible. We can sort of ignore that, but that thing times time, cosine of that mess. Okay, so what does that mean? So these guys these are just some trig identities that we use to do that transition. Trig identities. Okay, so now, what that says is, what is the signal we're going to get out of this thing? We're going to get two things. We're going to get a signal that is basically an oscillating signal at the difference frequency, which is a low frequency. That's why we don't have to digitize it too rapidly, and a very rapid one, and that's the rapid one we filter out. So basically, so this guy, oh sorry, I forgot to put the parentheses over here. So this is 1/2 this whole mess. So basically, this guy is going to be what we want. So this is, this is the difference. So it's the frequency difference between the signal coming out of the brain and our transmitter frequency. Could be 0 if it happens to be exactly the same as the transmitter frequency. But typically it's going to be going up and down, oscillating back and forth between different frequencies, different frequency offsets. And then this one we filter out. So that's this guy. That's that one that's filtering this guy out. So filter out that guy. So we just want to keep the frequency difference. So that's the That's the bottom line. But we're not done yet because obviously we've still only got one stream of numbers here. So how do we get the second stream of numbers? So to get the second stream of numbers, we basically just multiply with a sine and a cosine. So this is a reference signal. So let's just draw this out again. So basically, if we have, so say we have, so this thing is what we would call a linear coil as opposed to a quadrature coil because it just has, it doesn't have like a sine and a cosine. It just has one signal. So our linear coil, so we take our linear coil. Oh, let me just, before I do that, let's just sort of draw this out. So basically, if we draw it out in terms of frequency here, what we've got, so our signal is, a pretty high frequency. It's got, there's several frequencies in there, but let's just assume it's one frequency. So that's a pretty high frequency. Our reference is the transmitter frequency, and that transmitter frequency is, we'll just assume there's one frequency there. Okay, so that's that slightly different frequency. And what the trigonometric identity says is our demodulated signal is going to equal the difference. So here's the difference in those two frequencies. And then it's going to have a really high frequency up here, which is, 2 times the center frequency, plus a tiny frequency offset. And so then what we finally do is we just filter this guy out by just letting low frequencies through, and then the thing that we digitize is, after filter. So this is digitize this guy. And so this guy is, just delta. So that's how we sort of get this delta frequency, but you've got a problem that we still need the second number. So where do we get the second number from? One coil. And so where we get the second number from one coil, so we've got this single coil. So here's this linear coil. And it's important to be able to understand that you can just get this from one coil. So we take that exact same signal, and then we send it up to this kind of circuit. That's phase-sensitive detection circuit, where you multiply it and low-pass filter it. And for this guy, we feed in the cosine. So here's the cosine of omega t. And then we get out of the phase-sensitive detection. So this guy is, let's just label this is phase-sensitive detection, phase-sensitive detect unit. So we multiply this guy by the cosine, and then we get a signal out of this. So this is the signal across time that's the real component. And then we just do exactly this. We take the same, just split the signal and then send it to another phase-sensitive detection unit that is multiplying it by a sine. And since this is the complex, so the thing about this is that it's a complex number with an imaginary, so this is an imaginary, the imaginary part of it. And so we would, if we're writing this out as a complex number, we would have to multiply this by I. An imaginary number, but it's not imaginary at all. It's a real, it's just a real set of voltages. And so this thing then gives us our imaginary data. So it's not imaginary. It's totally real. There's a total real set of voltages that comes out. Now we've got two voltages coming out. And so what do we do with those? Well, what we've got is basically, if this is a circle of radius 1, we've got some imaginary number, and here's the real part of it, and here's the imaginary part of it. So this guy, so the real part goes here, and the imaginary part goes here, and then that gives us, this angle here. That it's basically a phase angle of that complex number at each point in time. So if you think about what comes out of the linear coil, what comes out of the linear coil is just, is just a set of numbers that's just going up and down like that. And what's the problem with that set of numbers? Well, the problem with that set of numbers is if we say look at sort of a middle value here, we can't tell whether it's coming or going, right? So we can't tell if we this number comes from the fact that if you're lying in the bore this way, here's the precessing proton. So they're precessing around like this, and so you can't tell this angle from this angle. So those two angles will give you the same voltage. But if you're doing phase-sensitive detection, you really need to know, like, is it 90 degrees or 270 degrees? And so the only way to get that information is with this phase-sensitive detection circuit. Now, when you first look at this, you've only got one number, so it's just like, where does the extra number come from? Well, the extra number comes from the transmitter. So the transmitter sort of adds information into the single signal to make this double signal. And that's fundamentally how you actually sort of get the phase angle, and you distinguish, say, like 90 from 270 or 0 from 180, because you've got this additional information from the transmitter. And so that's, I always draw it out like just with a single coil. So this is a linear single element coil. Single element coil. And so so what does this actually look like in practice? So if we draw what the voltage that comes out of the brain, out of the entire brain, remember the signal equation is summing across the entire brain, so it's summing across the entire brain, and then it's causing a single number in this linear coil at each point in time. What does that single number look like? Well, it's going to have sort of this exponential decay, and it's going to be cycling up and down like a very rapid sine wave, but I haven't drawn anywhere close to the number of wiggles required. So this is 123 million per second. 123 million per second. So that's the actual signal that that comes out of the terminals of the coil. And so after we've done the phase-sensitive detection to it, we get a much lower frequency signal. So what does that lower frequency signal look like? So, well, it's got two parts. So it's going to have, and it will still follow the same envelope. Same envelope, but the parts are going to be, something like, it's going to be doing something like that at a much lower frequency. But it's got another part to it. So if that was the real part that came out of multiplying by a cosine, it's going to also have another set of numbers coming out of it that's actually multiplying by a sine. So here's that. So you'll have another set of, I'm not drawing it very accurately, but you'll have another set of numbers that are, so this guy is the imaginary part of the signal, which you get by multiplying by the sine, and this guy is the real part of the signal. So it's not an imaginary signal, it's a real signal, but this signal then is what we want, which is what is the instantaneous angle of the summed magnetization. So remember, we're still summing across the coil, so we're, there's local magnetizations all over the place, and we can't record the Z component, so we can only record just the part that's sort of perpendicular to the B0 field. But this is a really good number. This tells us what the angle of that number is around from 0 to 360 unambiguously, which over here it's ambiguous. You can't tell, like, 270 from 90 in this single coil, in this single real valued signal. So what does that actually correspond to? Just think of this very concretely. So let's just go to some part of it. So let's take, like, say, this number and this number. What does that correspond to? So that's a real number, slightly negative, and an imaginary number that's positive, a positive imaginary and a negative real. So, what does that correspond to? Well, let's just draw, let's draw it out below. What that corresponds to is as a vector. So if it was slightly negative real over here, and then a positive imaginary, so we would get something like that. So that point, corresponds to a vector like that. Now, if we go a little bit later, say, like, let's just take this one right here. So that one had a zero imaginary and a negative real. So that's 0 imaginary and then negative, sorry, I'll do it the other way around, sort of negative real and then 0 imaginary. So that guy's going to be a smaller vector. So that guy's a smaller vector because the total amplitude of that one is less. And so basically this is what you get out of the phase-sensitive detection. It's a long string of arrows, so at each point in time you've got a little vector and they're getting smaller and smaller as you go, further out. So that's the fundamental thing that you have to get about how you record this signal. So there's two things about it. One is that it's always a vector, and then the second one, which is confusing, it's always a sum across the entire brain. But it's not just a simple sum, it's a vector sum across the entire brain. So you've taken all the you've taken the XY component of all the local magnetization vectors across the entire brain, whatever their instantaneous state is, added them all tip to tail, and turned them into a single vector, and that's one of your data points. So that's the fundamental stream of data points that comes out of the MRI machine. And you can get this stream of data points, a chemist could get this stream of data points 50 years ago. But we absolutely require this complex valued data stream in order to actually be able to do to make an image. Okay, so what this corresponds to last time is we talked about when we had a complex signal. So here's our complex, we'll make it a bold one. So here's our complex signal at a moment in time. That complex signal was basically equal to the instantaneous XY magnetization amplitude, so like just the length of this vector, and then times the angle of the vector, and the angle of the vector was e to the minus I frequency difference times time. So just remember, so this way of rewriting it is slightly different than a vector. It just has, so this is the amplitude, and then this, remember this whole thing just stands for, a vector of amplitude equals 1. And so it's basically just an angle. It's just an angle, and then we've separated off the amplitude when we write it out in this sort of complex notation. And then, so that's the signal, that's the basic signal, but remember that signal, what did that actually come from? That came from a sum. And so this signal, was fundamentally, came from a sum across the brain. So, it was a sum, so this, this guy came, that's what we talked about last time. It was a sum across the whole object of, whatever the magnetization, the XY magnetization at a particular point in the brain, times whatever the oscillation at that particular point. So here's that oscillation, but that oscillation is space dependent, right? So that's another fly in the ointment. We haven't talked about that yet. That's the next lecture. It's space dependent. It's going to be different at different places in the brain, summed over the entire brain. So that was kind of like the point of the last lecture. We're summing across the entire brain a whole bunch of different frequencies. So there's different offset frequencies in different parts of the brain. The R vector means for a point in the brain. And there's different amplitudes of those vectors. So that's the sum across the brain part. But the bottom line is, what do we actually record? Well, we just record this, which is just a single thing. It's just a single thing. So this whole mess of adding all those different frequencies together ends up with just a single signal. And that single signal is, just a single frequency, basically. We'll see next time how we end up with this, how this entire mess can turn into one frequency. Okay, so in the last minute, just to completely sort of drive home the point, what if you have a quadrature coil? So you might have been thinking this whole time, well, why are we going through all this trouble? Why don't we just take a quadrature coil that actually records the sine and the cosine part of the oscillation? So, why don't we just do something like, you've got a head here, and, why don't we just say, why don't we just put a coil, over the head like this, and then put a sideways coil like this. And so this guy would record the sine, and this guy would record the cosine. So if you put an oscillating thing in there, these two guys would be out of phase by a quarter of a cycle. And so, that's basically a quadrature coil. There's a lot of different ways to make a quadrature coil, but that's one way to make it. So you might think, well, why don't you just do that? But just to give you some idea of, how this works, if you can understand this, then you can sort of understand the main thing. What do you actually do with a quadrature coil a lot of times? What you do is you take this signal from this guy, and we introduce a 90-degree delay. So we delay that guy, and then we take this guy, and we just add them together. So how could that work? And then we take that single signal, and then we send it through the phase-sensitive detection, and then we turn it back into real and imaginary. So that's actually how a quadrature coil might be wired up. So what are you doing here? Well, you're taking a signal you're taking a signal that looks like a cosine from the vertical coil, so here's a cosine-like coil, cosine-like signal, and then we're taking a sine signal, or a negative sine signal. Here, so there's our, let me draw a better sign. I delayed the wrong guy, sorry. Let's put the delay over here. Pi over 2 delay. Yeah. So I don't have to change my sign. Okay, so then, there we go. It shouldn't let me lecture about electrical engineering. Okay, so here's our cosine coming out of this guy. And here's the sine coming out of that guy. So here's our sine. And so what do? We delay the cosine by a quarter of a cycle. So here's the cosine delayed by a quarter of a cycle. And it turns into a sine. And then we add them together. So now we get like a bigger sine. We just get a larger signal. This guy's a larger signal. Then we send it through the phase-sensitive detection. So here's the phase-sensitive detection. We multiply by a cosine, phase-sensitive detection, and multiply by a sine. And then we get our real and imaginary again. Now, how could that be a good thing to do, to sort of take two perfectly good signals and mush them together? The reason this is a good thing to do is because the noise in these orthogonal coils is uncorrelated. So it's safe to do that. So we won't amplify any noise because we have completely uncorrelated noise in the two coils. So this is the way you might hook up a quadrature coil, and the reason is you just want to sort of minimize the number of wires, because if you delay them and add them together, then you only got one. This could be a long wire heading to the phase-sensitive detection, and so you only have one wire. So this just, so you can understand that one. Like the first, when somebody said that this is the way it works, it's just like, what? You go through all this trouble to get two separate signals, and then you just stick them together, and then you pull them apart again. But you don't lose anything doing that. You don't lose anything doing that. Now, this, I might have mentioned earlier that one of the ways of making better signal to noise is to use a smaller coil. That's a different concept. So like, one idea is that if you have two coils that are at right angles to each other, they're uncorrelated, but there's only two available right angles to work with. So there's no like three-part quadrature coil. The quadrature coils just have two phases. There's only two possible things that are perpendicular to each other in 2D. So that's one way. The second way of increasing your signal to noise is to go from a linear coil to a quadrature coil. But another way of increasing the signal to noise is to make a smaller coil, but that's a different mechanism. So smaller coil has better signal to noise, and the reason is picks up less noise from rest of brain. So that's a different mechanism from rest of brain. It picks up the same signal from a particular part of the brain that the coil is over that a big coil would pick up, but then it picks up less noise from all the rest of the brain. And so so this is one way. This makes the signal to noise go up by the square root of 2 when you have a quadrature coil versus just a single coil. This other one makes the signal to noise go up even more if you have a whole bunch of small coils, because each one is essentially ignoring noise from the whole rest of the brain and yet getting the same signal from the part of the brain that it's sitting over. It doesn't actually get a bigger signal. It just gets the same signal. So, okay, so I think I've reached the end here of the main points. So, we add up all these vectors across the brain that all have different frequencies. They all mush together in a vector sum kind of way, and then we end up getting this one signal, but it's a two-component signal. It's a two-component signal, so it's a vector at each point in time. It's got an angle and a length, and that's our raw data. And the way we get that vector is by this phase-sensitive detection business, which is take one signal and then multiply it by a cosine and a sine, and then that gives us this fundamentally two-dimensional signal, which is the angle and the amplitude. Okay, so David, we can finish the recording and we'll take some questions then.